Assalamu alaikum wa rahmatullah. So, as you know, basically, last time we made a very important discuss on the very special theorem in physics. That's the work kinetic energy theorem. Okay, work kinetic energy theorem. So, this is a kind of special tool in a way that when we apart from the Newton's laws, if we use this principle, this theorem, I can say we'll get the same demand, but in a quite short time. Okay, so in today's discussion, there is kind of another nice piece of physics issue. That's what we call as the conservation of mechanical energy. Conservation of mechanical energy. Okay, so first of all, it's very important to mention what the mechanical energy of the system is all about. As you know, the potential energy plus the kinetic energy. Okay, potential energy and the kinetic energy, the sum of potential and the kinetic energy for a given system, it is defined as the mechanical energy. Okay, so basically the mechanical energy, it is composed of two parts. One is a potential part and another is a kinetic energy part. Okay, when we sum up these two parts, we'll get the entire energy of a system, a whole energy of a system. That's what we call as the mechanical energy. So let me come to know how exactly under what conditions the mechanical energy of a given system remains conserved. Okay, so it's again here the moment to remind what we call as work done. And definition from that we will try to exploit how exactly this conservation of mechanical energy seems good. So in the previous lectures we used this equation number of times, the work done, okay, by means of the forces. Okay, so we got here the kind of this we got in last lectures, the kind of this instruction, and this is a definition of work done indeed in a more general way. Okay, so but when when I introduce the nature of the force for a bit, when my forces are conservative in nature, okay, at the same time I got one more equation for conservative forces. That's, I can say, the negative gradient of this potential, and this is what the conservative force definition is all about. Okay, number third was that when I am in the last discussion, I use a very important thing. That's basically the work kinetic energy theorem. From the work kinetic energy theorem, I got when work is done on the system, there must be the corresponding change in the kinetic energy. Okay, this is what this principle is all about. So if I will just use the two things here, these things are familiar to me whether I talk about this or this. So by using this thing, I will come to the conclusion, right, how the mechanical energy of a given system is going to conserve. Okay, for that, where from I will start, I will use these definitions here basically. So last time when we discussed this work done by the conservative forces, basically, yes, work done by the conservative forces, it's nothing but the change in potential energy. Okay, minus of the change in potential energy. And this is the thing that I got from the last moment. Okay, so if initially my particle has the potential energy U1, at some later time a particle potential energy is U2. So if I would write it in a more simpler form, I will get my work done. Yes, it will be, yes, this subscription means that there are the forces which are basically the conservative in nature. So by this way, I will get change in means U2 minus U1. Okay, this is how we literally write down the change. So it will be, yes, U1 minus U2. Okay, so this is a work done by the conservative force. But if conservative forces are acting on a system, it must give the corresponding change in the kinetic energy for the particle motion and all that. Okay, so if my final here my work done, I can write it as K2 minus K1. Okay, this is what we call as the change in kinetic energy. So this is a work done by the same forces at the same time. This is a work done by the same forces, and this corresponds to change in potential energy. So if I will equate these two, I will get here, yes, my U1 minus U2 is basically K2 minus K1. Okay, or I can write as U1 plus K1 is equal to U2 plus K2. If I will remind here once more the definition of mechanical energy, yes, mechanical energy, it is defined as potential plus kinetic energy, okay? So here basically what I can write it as, E1 is equal to E2. Doesn't matter for me if there is some E3, means that I can say it is constant in general. So if I will state it here, if my system it is acting upon by the forces which are conservative in nature, so under this situation, my total mechanical energy for a given system, it is constant, okay? So this is what we call as a conservation of mechanical energy. This is the reason basically why we call conservative forces as such, because they conserve the total mechanical energy of a given particle. So you can define here the conservative forces like this way. The forces, under the action of forces, okay, if the total energy of a given system is going to be conserved, so we call forces must be conserved in nature, okay? Forces must be conservative. Conservative forces are such under which the total mechanical energy of a given system is going to be conserved. It's again the well-known conclusion from the forces which are basically the conservative ones. Okay? So if the conservative forces are going act on a particle, so under this situation, under this way, we can safely state it like its total energy will be constant. Okay? This is what we call as the conservation of mechanical energy. So we got here the important statement right now, if the total mechanical energy for a given system is going to be conserved, so the forces which are act on a system, they must be conservative in nature, okay? So conservative forces by name, they are called so because they conserve the total mechanical energy of a particle, okay? So it's the right moment to look and focus on the name of this force is why it's called a conservative. It is because it basically conserves the total mechanical energy of a particle, okay? If I will do the simple problem on yes, and the mechanical energy of a particle, okay? If it is given in a problem like we have the particle, its mass is 1 kg, okay? If my particle, its mass is 1 kg and it moves freely under the potential energy, one-dimensional potential energy, if this is my particle mass, okay, and my particle moves freely under one-dimensional potential energy, if the form of potential energy is given like x4 by 4 minus x squared by 2 joules, okay? This is a potential energy associated with the particle and its mass is 1 kg, okay? If it is also given in a question that the total energy of a particle is supposed to be 2 joules, okay? If this is my total energy of a given particle, as I know total energy is sum of kinetic plus potential energy, okay? This is what we have discussed so far from the view of mechanical energy and all that. If the question tells me basically what's the maximum, what I can say, the kinetic energy, okay? What's the maximum kinetic energy for a particle? If I will just state my problem here once more, the particle mass is given and it moves freely with some potential energy this. If the total energy of the particle is this much, but problem basically tells me what's the maximum kinetic energy associated with the particle. If I will guess what's the content from the problem, I can guess it this way. If question tells me basically I need to calculate the maximum kinetic energy, obviously my potential energy should be minimum. This is the kind of guess I can make at the first place, okay? When kinetic energy will be maximum, my potential energy should be, minimum. This is all I can say. And at the first view, how I can look the problem, this is what I can guess, okay? So, if I write my U plus K, it is basically E, okay? So, U is given, E is not given, and E is also given, that's the total energy, K is not given, okay? But not only K, I need to find its maximum value. How I can find its maximum value? When kinetic energy will be maximum, okay? This must be minimum, okay? From the law, if you remind the last discussion, if my potential energy will be minimum, means that its derivative should be minimum with respect to x, okay? Because potential energy is a function of x here, so its derivative should be minimum here. Sorry, derivative should be 0 for the minimum potential energy. As basically question gives me the kind of internal hit, like I need to calculate the maximum kinetic energy. For that my potential energy, it should be minimum. Okay, so if my potential energy will be minimum, so I can say that its derivative with respect to x must vanish. Okay, this is the thing that we have discussed number of times in the previous lectures and all that. So if I will use here, if I will operate the potential energy function with respect to this operator, and it's x4 by 4 minus x square by 2. Okay, this is a given potential energy for particle. So if I will just differentiate it, yes, but its right hand side must be 0. By this way I will get the value of x. I will opt to the value of x, that will be the corresponding value of, it is only unknown here when I will get it. So E is given, so I don't need to bother about might. By this way I will get the value of energy that will definitely represent its maximum value. So here if I will just integrate it, after integrating a bit, I will get here is 1 by 4x cube minus 1 by 2x is equal to 0. This will go with this and this will go with this. My x cube is basically equal to x, and it will go, my x is equal to x square will be 1, so my x will be plus minus 1. Okay, these are the values of x for which my potential energy will be minimum. Okay, because here it's not mandatory to go for another derivative, whether I will put plus 1 or minus 1, both will give me the same result, because it's an my x is an even powers of this and this. So I will get here something like the same thing. So whether I will take here minus 1 plus 1, so under both situations I will get the same value for minimum. Okay, here if I will just rub it for a moment, so what was given in a problem is x4 by 4 minus x square by 2 plus k, it was given as 2 joules. Okay, total energy. So for this max, I have to opt to the value of this. For k max, it should be yes 1 by 4 minus 1 by 2. Okay, is equal to 2. So for k max, if I will take the sum of this, it should be yes minus 1 by 4 equal to 2. So k max will be equal to yes 2 plus 1 by 4. It should be 9 by 4 here. Okay. So what it will be is, my k max, it will be 9 by 4. Okay, my maximum kinetic energy of a given particle, it will be this much. Okay, if I want to know maximum velocity of a particle, because I will use the further content given in the question, it was given like 1 kg of mass. Okay, so I will use the definition of kinetic energy 1/2 of V max square. Okay, I can find this way the maximum speed of a particle. This 2 will go with this. Hope you are getting it. This is 1 here. It's V max square. It's 9 by 2. Okay. So my V max will be simply, yes 3 by root of 2. 3 by root of 2 meter per second. This is what I got from the given question after using everything from the question. Like, at the first place I got the value of maximum kinetic energy. After that I should find the maximum, because it's also given in the question what is the mass. Mass is 1 kg. By that way we can find maximum speed of a particle. Okay, my particle moves with the maximum speed. This if it has a potential energy of a given, and the particle total energy is given as 2 joules. Okay. So if I look to the once more, if I will just remind here once more, what's called that work kinetic energy theorem. What's the more general remarks of this theorem? This is my here point of interest right now. Okay. Basically, if I look the more general remarks of the work kinetic energy theorem, so what's that basically? There is some important thing that I need to discuss about this thing here. Like if I will just state this work kinetic energy theorem here once more, this work done, it corresponds to the change in kinetic energy. Okay, this is what we did from the last lecture. Okay, Now, if the system is acting upon by both, if the system is acting upon by the both, means work done by the all forces or the total force, they may be the conservative one or they may be the non-conservative one. Okay, if my system it is acting upon by two forces, one is conservative, another is non-conservative. Under this situation, again I will have this change in kinetic energy. Okay, if my system it's acting upon by total force may be either conservative or the non-conservative. Okay, if it is acting upon by total forces, means there will be the work done by the conservative forces plus work done by the non-conservative force. Okay, it must lead to the change in kinetic energy. This is something that we got from the last story and all that. If I want to know how exactly this theorem or this principle works under a different intuition and all that, so if I will put my WC here, it will be negative. Okay, as I know from the last discussion is also work done by the conservative force, it is negative of the change in potential energy. Okay, this is something which is known to us right now as we did it. So here work done by non-conservative force, it's change in kinetic energy. Here it's yes plus the change in potential energy. If I would remind just my story here once more, if I want to know the total work done with the total force, means work done with the conservative force and the work done with the non-conservative force, what's my point of interest here? Like, I want to know the more general remarks of this theorem. Okay, so here I mentioned work done with the total force, they will be the conservative and they will be the non-conservative here. So this corresponds to, this leads to the change in kinetic energy. Here work done by non-conservative force, it will be this much, and I will just transform it here. If I remind what I discussed from the previous videos with the work done by the conservative force, it is equal to the minus change in potential energy. So here I got here something. If I write U plus KE, you know that potential plus kinetic energy, it's a mechanical energy. It's a mechanical energy. Okay. So my work done by non-conservative forces leads to the change in mechanical energy. Work done by the non-conservative forces leads to the change in total mechanical energy of the system. So here, if I write it here, work done by non-conservative force is equal to the change in total mechanical energy of the system. And this is, by the way, more general remarks of what we can say the work kinetic energy theorem. If I will use this unconditional theorem here, but if I will just presume my condition is here, if it's given in a question that my system it basically is acting upon by the non-conservative forces, by that way I should look what will be the corresponding change in total mechanical energy. Okay, this was basically the general remarks of this theorem that we have discussed in the last lecture and all that. Okay, so this is a very important thing here to mention, like when my system is, if I look by work done with the non-conservative forces, there must be the corresponding change in the mechanical energy. Okay, under the condition of non-conservative forces, we have this much. So it's very important thing that we got here. Okay, so basically if we'll do some the simple problem of this type that involves basically the non-conservative forces. Okay, if I want to know what's the work that's going to be done by the non-conservative force, at the same time I should look the change in mechanical energy. I should look it in terms of the change in mechanical energy. Very important. So if I will just mention here the problem, like if there is a some inclined plane, okay, a rough inclined plane, have some inclination theta. Okay, if this side of plane is rough, okay, and let us assume that it has a length L and this vertical length is here H. Okay, if my block is here at the topmost point, okay, if the block mass is M, it is going to lie on this rough incline, okay, of length L. If I want to know when the block reaches at the bottom, what will be the velocity of this block? Or I can say what will be the speed of this block when it reaches at the bottom. Initially, bottom rests at the top of the rough inclined surface, okay? So if I will just, look to this case, I can find the velocity or the speed of this block when it reaches at the bottom by using the Newton's laws. Okay, but that will be the quite messy for us. By using the laws of motion, it will feel the kind of messiness, because we need to integrate the equations of motion and all that. That's means we should care about much over the terms. But if I will use this thing here, I need to know only one thing. If there is a non-conservative force, then it must give the it must make the corresponding change in the total mechanical energy. Okay, if I will just parameterize my problem here, if system is initially at rest, if my block is initially at rest, what's the initial kinetic energy? If I will just represent it by K1, it must be 0. Okay, now my block is at a vertical height h from this reference, means that my U1 is basically what, how much? mgh. Okay, and this is what I can know at the first place from the problem. Right now, when block it will reach here, obviously its potential energy at this point will be 0, because height will be 0 at this point. My potential energy in the case second will be 0, and what will be the kinetic energy in the case second, that I don't know. Okay, this is the thing that I will just calculate here first. Okay, now if I want to know basically when my block will be in this way at any instant of time. If my block will be here, okay, there is frictional force that will act on it, and frictional force is a type of non-conservative force. And only thing I want to know here, how much of work that's going to be done by this frictional force, and it will lead to the corresponding change in mechanical energy. This is a kind of insight that I need to take the consideration of this thing here. By this way, I can calculate with which speed, what will be the speed of this block when it will reach at the bottom. Okay. For that, I will just first of all calculate what's an amount of work done that will be done by, what's an amount of work that will be probably done by the frictional forces. If the frictional force will be along this direction and it will displace in this direction, means my force and displacement, they are anti-parallel to each other. Angle is 180, cos of 180 will be yes minus. So work done here in this case, it will be yes minus F over L. Okay, if I will do here one thing under the notion of free body diagram, this is the weight of a body. Its one component will be along this direction, it will be mg cos of theta. If this is theta, this will be theta as well by geometrical argument, and here will be my normal force. Okay, by definition, normal force is something which is perpendicular to the surface. Okay, contact. So here if I will use again the definition of frictional force, it will be yes mu k n. Okay, it's not the static friction that basically when block will be released from this position, so static friction is not able to hold the block at this position. Probably it's a kinetic friction that will take the part here. Okay, so it will be yes, it will be minus mu n L. Okay, not only this, but it's mu k here, coefficient of kinetic friction. So if I will just look at the problem here once more, basically the motion is going to be have for a block along this direction. There is no motion along this way. Just look to my hand. Basically, if I will just making the movement of my hand upside down from this way, so there is no motion along this way. So from this kind of conclusion, I can guess it here. The forces along this way around, this should be balanced in pairs. Okay, it's your cos of theta. So my basically n minus mg cos of theta, it must be 0, because net forces along this direction is 0, because my motion is not going to be for a given block along this way or this way. So by this way, I can get the value of my normal reaction or normal force. It's mu g cos theta. Here, if I will put it here, it will be mu g cos theta L. Okay, this is my work done by the non-conservative forces. Okay, my work done by the non-conservative forces, I will have, if I will use it here, so what I will get, yes, I got something very special here. Right now, the work done by the non-conservative forces, how much that is. Under this case, yes, it is something like mu k mg L cos of theta. Okay, if I will just number it first. But what's the change in total energy? Change in total energy, it will be E2 minus E1. Okay, so in the case second, my energy is kinetic. In the case first, my energy is potential. That's mgh. Okay, so here K2 will be equal to yes. K2 will be equal to yes. Yes, it will be minus mu k mg cos theta L is equal to yes K2 minus mgh. Okay, I can write the definition of the kinetic energy. It will be yes V square. Here it will be yes mgh minus mu k mg cos theta L. Okay, if I want to know my V here, it will be yes under root 2gh minus mu k L, yes, cos theta, 2 mu k L cos theta. Okay, yes, 2 mu k gl cos theta. This is the velocity with which, this is the speed with which the particle move when it reaches at the bottom. Okay, so this was all about, I mean, the conclusions from and the remarks from this work kinetic energy theorem and all that. Thank you.